morning, everyone. I would like to welcome you all to today's webinar on the topic, How can chemical engineers shape the 21st century? Today, we have with us Dr. Murali Rangarajan to deliver the session. Dr. Murali Rangarajan joined Amrita Vishwa Vidyapeetham in December 2007 after completing his PhD in chemical engineering from University of Florida, USA. He is the Head Center of Excellence in Advanced Materials and Green Technologies and is working as Professor, Department of Chemical Engineering and Material Sciences. I cordially invite Dr. Murali Rangarajan to deliver the session. Over to you, sir.
Good evening, everybody. Happy New Year. And thank you, Ms. Nija, for those kind words of introduction. This is a fantastic topic, actually. When I was suggested to give a webinar on this topic, how can chemical engineers shape the 21st century? Very exciting topic. Let's delve right into it. A brief outline of the presentation is going to be, first, we are going to try and understand what chemical engineering is. Unfortunately, as you will see, there's a lot of misconception about what chemical engineering is. And we'll also look at what chemical engineering isn't. We'll look at who are chemical engineers, what do chemical engineers do and how do they do it? What do chemical engineers make? What skills do you need to be a successful chemical engineer? And then we will get into the topic, how can chemical engineers shape the 21st century, which will be the major portion of today's webinar. And then last but definitely not the least, we will talk about the Amrita advantage. How does Amrita prepare you to become a person who shapes the 21st century as a chemical engineer, a successful chemical engineer? With that outline, let's first try and understand what chemical engineering is. These days, in the late 20th century and early 21st centuries, there are some universities in Europe which have started calling this domain not as chemical engineering, but as process engineering, as it rightly should be called. One of the correct names for this discipline is process engineering. And we'll try and understand why that is with a simple example. Consider cooking a South Indian meal. So you have all these raw materials which you combine into fantastic product that is excellent, very tasty to your palate, and very interesting to eat, right? So that is this process of conversion of all these raw materials into value-added products, and that is the engineering of chemicals, because all of these are chemicals, all right? And that is how the name chemical engineering came about, all right? So the focus is per se on the process of converting this raw materials into value-added products. And what sort of systems do we have to create for accomplishing this conversion? That is what chemical engineering is all about. And therefore, many of us I'm including myself, we walk into chemical engineering because of our interest in chemistry, while sure enough, there is food everywhere in cooking, all right. The cooking process is sometimes quite different from the food itself. Not one who's really a connoisseur of food does not have to be a great chef. You understand the difference, right? So the skill sets required are slightly different, and it's important for us to understand what a chemical engineer is, who a chemical engineer is, and what she or he does, and what kind of skills does one need to be a successful chemical engineer. So with that background, we start looking at these questions. Who are chemical engineers? So therefore, here is my take on who chemical engineers are. Chemical engineers are the chefs of industrial processes. We convert raw materials through industrial processes into value-added products. So how do we do this? We start with procurement of raw materials, design and optimization of the various processes stepwise. Each process, you don't go from the raw materials in one process to make all that delicious food. You have to go through so many processes. So each of them has to be designed and optimized. And then where is this process going to take place? It's going to take place in these vessels, in these big equipment. We have to design and optimize the material needs and energy needs for the process. How are you going to supply energy, heat, cool, flow, precipitate, condense, evaporate, whatever. And how are you going to place all these equipment in the industry? You have to design a layout of all of that. Then we have to fabricate all those equipment, install, test, of course, after testing, installation of the equipment, commissioning of an industry. Then once an industry is up and running, you have to produce the continuous production of the products, value-added products. So troubleshooting there, quality control there, management of the production process itself. Packaging the products, that's not always obvious. Food packaging is the epitome of our understanding. Easy to understand why packaging of a product itself is an engineering in itself. And then, of course, we have to look at marketing, sales, supply chain, logistics, all of this. So there is engineering. There is so much more than chemistry, as you can probably very quickly realize in chemical engineering. And of course, there is new product process development. There is all the research and development that takes place. So that's also very much part of chemical engineering. So what products do we make? What do we make? Literally, if you look at it, practically everything out there is made of chemicals. Starting from molecules, this is a docking of something like a virus or something like that to some protein. So starting from such molecules to very complicated rockets, to clothes, to fast-moving consumer goods, to pharmaceuticals, to chocolates, to food, to electronic gadgets, to you name it, everything, fuel to paint to electricity, everything, fertilizers. We are universal engineers. So the concept of translating raw materials into value-added products can be taken to a whole host of domains. And therefore, this is very crucial. This whole understanding of chemical engineers or process engineers as universal engineers. So we are the people who sort of hold the keys of the whole processes, so to speak. And then we design an equipment that is manufactured by a mechanical engineer. We ask for a certain electricity specifications that is provided for by an electrical engineer. We ask for a voltage pattern, current pattern, whatever, and that is delivered to us by an instrumentation engineer. We ask for certain specifications for controlling processes, large-scale processes, which then are computer-based control systems are there, and the optimization and the use of AI and all of these are handled by computer science engineers. And nowadays, with all the multidisciplinarity, it has become very critical for us chemical engineers to also become multidisciplinary. We are at the heart of all of these. This whole scientific advancement, so to speak. And therefore, if we have to become successful chemical engineers, first and foremost, before we write any of these skills, we need to sort of first embrace interdisciplinarity, multidisciplinarity. We should be ready to go and sit and learn anything that's out there. And then we should be able to take our skill sets of converting raw materials into value-added products and apply it in those specific contexts. So how do we do this? Mathematics is the language of science, and that is very critical. That is the first and foremost language with which we learn to communicate, so that there is no ambiguity, there is no vagueness in our communication. 1 + 1 is always 2. There is no 1.99 or 2.01. And this is important so that, there is precision, there is accuracy. Drawing is the language of engineering, visualization, geometry, that is crucial. Then the next one is the basic principles of physics, chemistry, and biology. We need to know what's happening in any given application, what we want to happen, and how to make it happen. So, and then we need to be able to keep track of stuff. So we need to be able to do statistics and accountancy. By accountancy, I really mean, you should be able to know what went where, really. right? So we are not dealing with accountancy in terms of money. We are dealing with accountancy in terms of materials and energy. All right. So is there no loss? Is everything accounted for? And then when we have very complex stuff which we have to handle in large scales, we need computer literacy and programming, and end-to-end interactions starting from your end customers all the way to the other end, which is basically your investors who have to give you the money so that these kind of processes can be developed. We need to have excellent professional and technical communication. And the most important skill of all, if you have this skill, you will be able to use all these skills that you pick up. And that is a skill called common sense. Unfortunately, it's not emphasized enough, in my opinion, in engineering. Most engineering is common sense, and therefore, it is not very difficult. But we just need to not complicate things unnecessarily, and then you just look at it with common sense. You will figure out what's happening and what needs to happen. Right. So we get to pretty quickly, took about 10 minutes roughly. How can chemical engineers shape the 21st century? And at this point, I would like to, spend a minute highlighting to you that it's important for us to understand the breadth of chemical engineering, and therefore the answer to how chemical engineers have a major role to play in 21st century comes from that breadth. So you can see a whole host of areas, whether it is climate change, healthcare, clean energy, clean water, clean soil, sustainable agriculture, defense and space, waste management, infrastructure, electronics, IoT, AI, big data, quantum computing. We have footprints everywhere, and that's crucial for us to recognize. So let's start with these various domains. Before I just get started with each of them, I'm going to start with healthcare and medicine first, as we saw. Since there are literally 3, 6, and 9 and 10 domains, really, if I even spend 5 minutes on each, it would take 50 minutes, and that's all the time that we'll have then. And therefore, I have to necessarily speak at a big picture level, and I have to give you 1 or 2 specific examples rather than go into the depth of what all is possible. But I can, through illustrations, give you a sense of what all is possible. And that's what I'm going to aim for these next 30 or so minutes when I cover these different areas. Okay, so let's start with healthcare and medicine. Some of these examples that I've put here, by the way, are activities that are taking place at Amrita itself. And I will highlight those, that these are activities, both these, for example, are activities that are taking place at Amrita. All right. And this is important for you to recognize, so that you recognize how Amrita is at the cutting edge of development research in the 21st century. Right. So one of the applications, one of the next generation applications is point of care healthcare devices. So if you want to monitor health properties, you should be able to do it at the point of care. Typical good commercial example that we have is the glucose monitoring strips that you have. You just prick, to get a drop of blood, and then that goes on a strip, and then that's inserted into this kind of a device, and then it gives you a reading of how much your blood glucose level is. And this is invasive. You prick and you get blood, and there are many such sensors which are non-invasive, like oxygen saturation. I don't know if any of you had to go through COVID related issues, or anyone in your family. This was something that pulse oximeter became so popular. People could just buy and keep it and then check. When I got COVID, I used to check my oxygen saturation levels 4 or 5 times each day, as per the doctor's advice. So that was one very common thing. BP measurement is another, blood pressure measurement is another point of care. But these are all general purpose properties with only one specific property, which is glucose level. You look at, these days, if you go and do a master health checkup, there are some 70 odd tests that they do. And all these tests can be carried out. There is absolutely no reason why they cannot be carried out at the point of care. That means you have to convert an entire lab onto a very small little strip or a chip. So there is some sort of a miniaturization of the entire activities that take place in a lab, and that all those activities are collected and collated, and they happen on a small chip. So the driving force for point of care healthcare devices is lab on a chip, the concept of lab on a chip. All right, so here you see this chip. This is a PSOC actually. You do a whole bunch of different types of measurements, and I've put a specific type of measurements called electrochemical sensing, and this is something that happens both in my lab as well as particularly in one of the labs in the Department of Sciences, where Amrita has one of the most renowned US patents in blood glucose sensing using non-enzymatic substrates. So that lab has also developed patents for cholesterol, for creatinine, for a variety of parameters. So specific parameters that you can monitor at home. And these non-enzymatic sensors are much cheaper, and they last a whole lot longer than enzymatic sensors. They can be stored much easier. There are these kind of advantages. Magnetic drug targeting is a personal interest of mine. This is a very fascinating concept. You use a magnetic field. You load your drug into some sort of a nanoscale or microscale, vehicle or a carrier. This is a particle. You have a polymer coating, and then you immobilize the drug onto the polymer coating, and then you inject it. If this particle is magnetic in nature, then by applying a certain type of magnetic field, all these particles will be collected towards the magnetic field, and then you move the magnetic field where you want to, and then you can target the drug as well as these particles to where a specific site where, for example, it could be a cardiac system where there may be a block and you want to sort of dissolve a block, or you may have this need not even be a blood vessel. It could be a renal system, that could be a stone in the kidney or whatever it is. So that could be a stone in the gallbladder, for example. So many things, right? And then the point is, once you keep that magnet at that position, once you've reached the location and that drug slowly gets released, there are ways chemistries that can be played with to ensure that this happens. And once the drug is released and you know that the block is dissolved or whatever, then what you do is then you move the magnet back and therefore collect all these particles back, and then wherever to the site where you injected them first into the bloodstream or any of the other locations, and you collect it all out. So this is a very interesting way of doing things. Of course, I have presented it in a very idealized fashion. There are lots and lots of issues with these, and we have highlighted some of those issues and tried to work on some solutions in our lab. This is about 4 or 5 years ago we worked on this. There is this whole lot of drug design and discovery that's happening. Candidates for drugs, medicines, for vaccines also, for example, all right, which site on your RNA or whatever it is, your DNA, depending on the virus. With COVID, it's RNA. Right? Should you target your vaccine and whatnot? And all of this is driven primarily by AI, and there is huge amount of data, and people process those data, and there is multiple aspects to this drug design. You look at pharmacokinetics, you look at pharmacodynamics, you look at what are the specific ligands that's what I was trying to talk about. Which part of your the target should you focus on, and there is all this structures. So you look at this docking, screening, and then you create all these databases. And this is a fantastic area. Amrita is doing a lot of work in this area, both from our School of Engineering as well as from our School of Pharmacy as well as from a School of Medicine. So it's a very extensive activity that is happening. Vaccines production. This is something we all awoke in terms of our realizations that this is a huge chemical engineering process. These reactors, massive reactors, and these massive centrifuges. I remember reading last year that Bharat Biotech for Covaxin procured the largest batch reactor to where the vaccine was produced, and this is just I think it was some 10 lakh liters or some capacity. It's insane volume. It's a batch process. You have to maintain the conditions so carefully. Everywhere conditions have to be uniform so that the production, the batch is of uniform quality, and so that you don't have any kinds of other issues. These are very sensitive materials, and they interact with our body, which is even more sensitive, and therefore the level of quality control in pharmaceuticals as well as in vaccine production is extraordinary, simply extraordinary. And India being a country which is a global leader in vaccine production today, and it's not just the Covishield and the Covaxin, a whole bunch of other vaccine candidates. This is nothing short of astounding. This is a testament to our skills, innate skills, as not only chemists and biologists, but also as engineers, and specifically as chemical engineers. We are cut out to be very good chemical engineers, and it bears out. There is a lot of history in this. Some other time, some other occasion, I'll be happy to talk about. PPE protection kit, and this is of course, again with COVID, a very major deal. Oxygen concentrator is another major deal, and this one that you see here is an oxygen concentrator that was developed in the Department of Chemical Engineering and Material Science at Amrita Vishwa Vidyapeetham in the early months of April, May, during the second wave, during the Delta wave of COVID-19. And this was funded by the Indian Navy. They want to use this oxygen. They want to sort of do a CSR kind of a thing, corporate social responsibility kind of thing. They want to sort of transfer this technology for free to various small scale industries, so that very quickly, you can scale up production. This oxygen concentrator is capable of providing sufficient oxygen for 2 patients at a time, up to 15 to 16 liters per minute. And it cleared all the tests, product specification tests, and all the tests that Navy had to put it through. The faculty concerned went to Visakhapatnam and handheld the transfer of technology, and not just for oxygen concentration in healthcare and medicine, but I'm skipping some sectors here. When we come to defense and space and strategic, this oxygen concentration is a very crucial process in submarines, when there are all these naval force members who are cooped up in this small volume. So oxygen concentration is a big deal for Navy, even otherwise. All right, so that can provide a good oxygen concentrator, which then can provide oxygen supply inside the submarines. Can provide additional crucial time before which the submarine has to resurface. So this is something that we are going to be working in close collaboration with Indian Navy for to customize this design for submarines and a whole host of other applications. 21st century medicine is not just about pills and all these high-end technologies, but also understanding how foods that we eat, going back full circle to our ancestral understanding, ancient understanding as to how foods that we eat provide health. All right. So there are these 2 types of food related components that are gaining a lot of attention. One is nutraceuticals, and the other is functional foods. So here is an example: carotenoids are immune boosters. They prevent macular degeneration. Catechins reduce the risk of heart diseases and certain types of cancers. Chocolates, interesting. Note that. Huh? Flavonoids maintain brain function and heart health and so on and so forth. There are so many compounds. I've just put some examples here. Right, I think I took a lot of time on healthcare and medicine. I'll have to make up for that in other domains. Climate change. By the way, there is a lot of work that is happening on functional foods at our Coimbatore campus. I collaborate with a couple of faculty who have expertise in nutrition, food science and nutrition in that area. Right. So there is carbon dioxide capture. That is one big deal. There are various technologies: absorption, adsorption, cryogenics, membrane, microbial algal systems, and also electrochemical technologies that are available. This is a very core, crucial chemical engineering technology. It's called PINCH. I'll just very simply explain what this is all about. This is consider a very complex industrial setup. There will be lots of streams that go in. Some, stream by stream, I mean some material substance that goes into some sort of an equipment where it undergoes some sort of a process. Let's not worry about what material, what equipment, what process, and it comes out. And all these streams that go in and out and in and out through so many equipment, they may get heated, they may get cooled, their temperatures may change. Now, you want to heat a stream, all right, suppose you have a process in which you want to heat a stream to say some 60 degrees or 80 degrees Celsius or whatever. In another process in the same overall industry, say you have another stream that comes out at 90 degrees Celsius, which you are just discarding or letting go, say. Okay, so what you may do is it's possible for you to then take the hot stream, cool it down, use that excess heat that hot stream has to heat up the cold stream which you want to heat. So basically, this is sort of pinching pennies, so to speak. This is sort of savings. It's simple enough that you can say, hey, you know what, I can do this when you have two streams. Say there is a hot stream, there's a cold stream. I can use one to heat the other. But when you have literally hundreds and thousands of streams that go in and out in a very complex chemical industry, how do you know which ones to pair up with which one else? What is the best way to improve the energy utilization efficiency of your process? Not just energy efficiency, energy utilization efficiency of your process. And in order to do so, suppose there is a cold stream, there is a hot stream, or whatever, all right? So you got to see how to match these streams in such a way that maximum efficiency energy transfer happens with minimum amount of effort. So this process is called pinch technology, and this is very crucial. You might wonder, what has this got to do with climate change? This is one of the world's recognized pillars in net zero carbon emission technologies. I hope you all know that our Prime Minister committed to making India zero carbon emission by 2070, and pinch technology, one of the major pillars for reducing industrial carbon emissions. Because when you heat a stream, what do you typically do? You use some form of energy, and that some form of energy as of today is still largely fossil fuel based. And even when you use renewable energies, and we have really not come to that, we are going to see that in the next slide. Even when we use renewable energies, it's not always zero carbon emission. So therefore, pinch is something where there is no external source used. It was used for something else, and then I'm using that reusing and reusing that kind of heat. This is a huge carbon reduction, emission reduction, low-hanging fruit, really. It requires a lot of optimization. It requires a lot of considering various scenarios. It requires some programming, some mathematics, some optimization. But you get into this, you're going to make a huge impact. And this is, doing this globally across various industries, not just chemical industries, but various industries. This is a huge deal, right? And this is a major pillar for carbon emission, climate change. So I was telling you the next slide is going to be about energy utilization in industries. People talk about electrification, rural electrification, penetration of electrification into the last mile. Goodness gracious, did you know most of the chemical processes use either coal or natural gas or oil to heat up furnaces. You've studied in your school, there are all these blast furnaces, like metallurgy, steel production, for example. Excuse me. Cement, you have furnaces like clinkers are worked on in these. You have these huge rotating drums and all these things, right? Kilns and all that, right? They are all heated to very, very high temperatures. Did you know that almost none of them are heated electrically? Even today, BASF, SABIC, and Linde produced. This is basically steam. Heating. This one completely electrified at large scale for the first time just a few years ago. So just as we do need to take electricity into our rural communities, absolutely, we also need to take electrification into industries. But that's easier said than done, because the energy needs are so huge. If we don't use renewables, then we are only making things worse, because what are we doing? The same coal that we are burning here, instead of burning it here, you burn it somewhere else, and then you add up all the transmission losses and then use the electricity here. I'd rather burn the coal there. All right. So basically, if you're going to do this for this electrification, you better do it with renewables. And that is a crucial challenge. And the reason I put this up along with pinch is because these two are some efforts that we are undertaking now as a major international collaboration in our Department of Chemical Engineering and Material Science at Amrita, along with one of the top 100 universities in the world called Durham University in the UK. And we are working with what are called foundation industries. These are all the infrastructure industries like cement, steel, and whatnot, fertilizers, bulk chemicals, and so on and so forth. These kind of pharmaceuticals, these kind of industries, where we are talking about making these industries, they're making their emissions, reducing their emissions to driving them towards net zero emissions, right? So there's one major international collaborative grant that we have received, and we have started work on this, right? So we've talked about clean energy a lot. So you have a whole bunch of clean energy production. There is a lot of effort that Amrita is driving in terms of flexible solar cells. These are called dye-sensitized solar cells, as well as production of hydrogen from hydrogen is one of the cleanest fuels that's out there. And we are looking at both production of hydrogen from biomass, as well as production of hydrogens from alkaline water electrolysis and other hydrolysis techniques, all green hydrogen production, which means there is zero emissions at the end of all of this. So there is no other non-renewables that go into this. So it's a green production. So this is a major technologies. These are major technologies that we are working on. We are working in collaboration with some of the leading industries in India for hydrogen production. And then there is also the energy storage technologies. The hydrogen particularly is a very promising fuel, because its calorific value is some 30 times more than your conventional fuels that you have, and it's so light. The problem is that it's so light, so it occupies so much volume, right? This gas is so light that it occupies a lot of volume. So storing this hydrogen is a huge challenge. You have to compress it. So a 200 bar at pressure, it probably hard to see this here. It's 200 bar pressure. This is the size of hydrogen. The same hydrogen, if we condense it into liquid, it's about this. And then what we are looking at is, there is a group of researchers, my colleagues, who are working on magnesium-based hydrogen storage alloys. This is about they have reached up to 5.5+% weight percent storage, which already is above the target set by US energy agencies and Indian energy agencies. So there is a huge funding from an Australian company running into multiple crores. And this Amrita is sort of developing the technology for hydrogen storage for that Australian company. And there are other, of course, the most obvious one is a battery. This is a sodium ion battery here. Of course, you probably have heard of the lithium ion battery. This is the next generation of that. Amrita is also developing anode and cathode materials for an Indian company, battery company, for lithium ion batteries. And this is, of course, these are phase change materials. These are supercapacitors. There's a lot of work at Amrita that's happening on supercapacitors. So how do you utilize this energy? You generated the energy, you stored the energy, then you have to charge and utilize. That involves setting up grids. All right. There is a lot of strength in our electrical engineering department, and in collaboration with them and with another leading top 100 university in the world called the University of Newcastle in Australia. Amrita is setting up a joint international research center on energy electrification, particularly renewable electrification and decarbonization. So the sort of grids as well as the energy technologies that will cause decarbonization. So there is all these microgrids, there are large grids, there are these nano grids, so to speak, which is for a single household or some sort of small scale application. There is a lot of effort that's happening in clean energy with respect to Amrita. I need to really speed up clean water, soil, and sustainable agriculture and combining a whole host together. Focusing more on what Amrita is doing. Let me go a couple of slides here. Okay, just want to point out just how many emerging contaminants, pollutants have come up because of our lifestyle, human lifestyle, whether it is from the FMCGs, the fast moving consumer goods, or from the various pollutants, pesticides and insecticides that we use, or from a whole host of pharmaceuticals, nanomaterials, a whole host of drugs, disinfection byproducts, the Harpics and the Lysols and all those things that we use, microplastics, sunscreens and UV filters. There are a whole host of these that are all ultimately, you take bath, you take all these medicines and then you go to the restroom, and where does it all go? It goes with the water. So this is, while there are sensors for water quality, which will give you a pH or conductivity, suspended solids, dissolved solids, you don't have any details. Okay, what are there? If you really know about the kind of pollutants that are going into water these days, you'll find it very difficult to drink that water. Water will be perfectly colorless, odorless, tasteless, and then it can be completely poisonous. So it's a huge risk. And these days, we get all these water cans and who knows what's in that water. There is no quality monitoring of any kind. It's a huge, huge problem. What we are trying to do, therefore, is reliable monitoring. And here I'm talking about, real-time monitoring. There, in healthcare, we talked about point-of-care monitoring, right? Here, the monitoring has to happen in real time at sources, say, for example, at rivers or water bodies, whether it is a lake or wherever. Okay, you got to continuously keep watching, because continuously there could be sources of pollutants that can cause pollution. So the kind of sensors that you develop for one-time use and throw in a portable point of care device may not work at all in real life, because that sensor is not designed to survive in a harsh environment for, say, 3 months, 6 months, 1 year, or whatever. It's designed for one-time use, maybe a few times use at best. So this is a completely different paradigm. This work we are doing in collaboration with University of Trento in Italy and University of Barcelona in Spain, real-time monitoring of heavy metal ions. There is also soil moisture, soil quality. Particularly, we are focusing on NPK. Just a small little anecdote. You've all heard of this neem-coated urea that is being sold by the central government and the state governments now, and a whole host of industries to boost our soil quality, soil nutrition. And fortunately, urea is just one, nitrogen is just one of the macronutrients that soil needs. You also have the P, which is the phosphate, and the K, which is the potassium. And then you have a whole host of micronutrients. Farmers, because they don't quite have an awareness of what is needed, and they have this glut of neem-coated urea they have access to, they just indiscriminately buy neem-coated urea and start just putting it in their fields. In the past 6-7 years, nitrates, ammonium, urea, and a whole host of these nitrogen-related contaminants in agricultural runoff waters has become a big nuisance in India, right? So again, we need to go for the concepts. I'll just skip this. We just saw this slide a moment ago. The concept that we need to go to is called precision fertigation. This is irrigation, of course, which is adding water and the addition of nutrients that are needed as per a real-time measurement and monitoring of soil quality. Then you sort of close the loop and then sort of figure out how much of nutrients do you need, how much of these various, hopefully sustainable natural fertilizers that you blend or dissolve in water, disperse in water, which then goes into the irrigation of these particular fields. So this concept is the next generation in sustainable agriculture. And in order to do this, you need to be able to visualize. Here in this particular case, it's not just water distribution and quality. I'm not sure if you're able to see this clearly. It's not just water distribution and quality, it's water as well as the various nutrients that you need to put into the soil. So as what is not just a physical system, but also something that is monitored in real time, and then it is controlled using a cyber side. So this is the next generation concept in computer science that has direct applications which need chemical engineering based sensors. We are developing these kind of sensors, and I've just hired a postdoctoral fellow to sort of work on these NPK real-time monitoring sensors for soil and agricultural runoff water. So this concept of cyber physical system where you have robust, reliable, preferentially low-cost sensing, because if you go back to the picture that, oh my God, I have to go through all of these. I'm very sorry. If you go here, just in one field, look at how many sensors you need. Costs will be in sort of realizing these kind of technologies. You need really, really low cost outcomes. We just run right through this. Yes. So we need robust, because survive in harsh environments, low cost, reliable sensing. You need heterogeneous, very different kinds of environments, interoperable. You have to be able to communicate with a whole host of devices, energy efficient communication, and and then you have to have some sort of treatment, which is, if there is any problem, you need to course correct for it. And then how do you power all of these? You have to have energy efficient, sustainable microgrids. And then you close the loop. Actuation is where, you sort of say, I'm going to add this much water and it's going to have this much N, this much P, this much K, for example, right? So there is a lot of the systems level approach that we need to take. Here is another example. We are working in collaboration with our computer science friends, colleagues. This is a water distribution network. So, these days, Har Ghar Jal Jeevan Mission, there's a lot of digging of pipes, roads to lay pipes and whatnot. There is this old water distribution networks, and this is a very common sight. You will see that a pipe bursts, and there is just water flowing and flowing for hours together. Nobody ever knows. So, is there a way to treat the entire water distribution network as a cyber physical system, place at specific locations sensors, optimal sensor placement, and from there, can you detect events in real time if there is a leak, or if there is a pipe burst, or if there is some sort of a mud? Suppose there is an underground pipe and some mud sort of seeps into the pipe because of some cracks. So can we detect all these kind of events in real time? So we are looking at large systems which we have to be able to model, and we have to be able to study. So this is systems approach. So we were talking about chemical versus process versus systems engineering. Here is an example where in large scale process systems where multiple processes take place, we do need to take this big picture systems approach and then optimize at that level. That's also something that chemical engineers do. Emerging water treatment solutions. These are all fantastic zeolite molecules used in filters. That's an electrocoagulation setup that it's not from us, but we are working on electrocoagulation technologies ourselves. This is photocatalytic disinfection, and that's of course RO, which is very commonly used in many domestic applications. The biggest challenge here is it's a fantastic temporary solution, but it's a disaster in some sense because there is so much of water. For 1 liter of water that you drink, you reject more than 1 liter of water. And, we are already in a situation where the water demand in India is going to outstrip the supply nationwide, if you look at it, within the next 3 years. And in many places, it has already happened. We can't afford to waste 50% of the water, potable water. I mean, while this does handle all those lists of all those crazy chemicals that I just listed out there, RO today is one of the best technologies in terms of providing a safe drinking water, but then at a huge penalty cost. Right. So we are also looking at, for example, developing water filters using some really low cost materials. This is concrete, by the way. So one of my PhD students, he's working in collaboration with IIT Madras, some couple of professors there, and we are trying to come up with some sort of filters for removing metal ions from wastewater. Let's move on to infrastructure, construction, sustainable construction materials. Materials, by the way, is, as our department also indicates, is very much in the domain of chemical engineering. Material science these days is a separate discipline, but it evolved out of chemical engineering, and we still are very closely connected with the department. So there are these conventional materials for roofing, for example, it's tar or asphalt or metal sheets or whatever, and then there are these various non-conventional roofing. And in terms of walls, again, we have various fiber reinforced mortar, right? Recycled plastic. I'd be remiss if I didn't talk about our fantastic polymer based, faculty with the polymer background in our department. They're doing fabulous work. We'll see one of those slides probably in the next slide. Insulation, again, there's a lot of insulation, conventional insulation. Nowadays, there are all these more sustainable materials that are being looked at. There you are. So one of the other activities from our department that took place during the COVID period is two-in-one solution, a sustainable construction material being developed and then using recycled PPE waste. PPE kits were just mass produced like nobody's business during our first and second waves of COVID, and it's continued to happen. It's a necessity now, and our government and the worldwide, governments are right to tout their capabilities to be able to produce PPE kits in large numbers, but these are all polymer based and they are absolutely non-degradable. What do? You have mounds and mounds of waste that is being generated. So here the shredded PPE waste is mixed with sand, hot mixed and hydraulic pressed, and then we have made interlocking construction blocks, panels, floor tiles, and so on and so forth. And these can be easily, the colors can be changed, patterns can be made, and all that. So this is a technology that has been developed by our faculty from our Department of Chemical Engineering and Material Science. A disaster resilient infrastructure, even though we have not been working on this, there are materials that go into this, and I wanted to sort of point this out, and I've just chosen earthquake as one example, not more than that. So just that one example. Electronics and IoT. All right, Moore's law tells you that the number of transistors and microchips doubles every 2 years, and we are, I don't know, it's like 5,000 crores right now. This means we have gone from such systems. You should read this ad. This is really funny. A 10 megabyte hard disk. Okay, 8-bit microprocessor, standard 64 kilobyte RAM. All right. 12-inch monitor, okay, 132 column dot matrix printer, CPM star operating system, all of this for only $5,995. All right, this was way back in the 70s. That's where we started out. I mean, and we are where today? We are looking at Xeon E7s, 10 cores, 20 threads. Just the last level cache is 30 MB, up to 2 terabytes of memory, DDR3 memory. Where are we from where we started? That's Moore's law right there for you, right from here till here, right? So we are looking at 5 nanometer, chips, right? So if you go all the way from the circuit board to various package balls, to package substrate, to C4 bumps, to micro bumps, to various systems, and you go inside, you will start seeing these kind of various metals of very, very fine sizes. By the way, this C4 bumping technology for some very sophisticated defense systems were developed in our lab, my lab, rather, I should say, in our Department of Chemical Engineering and Material Science as a project which we did for DRDO, right? Photonic chips, right, and quantum computers, and that's all I'm going to mention. I wish we had more time. It's already 6:22. So much to speak about this, but just have to skip it. That's Google's quantum computer, by the way. A lot of portable instrumentation. This is a portable Raman spectrometer. That's a portable ultrasound device. This is a portable multi-parameter water quality monitoring device. Lots of these kind of electronic devices also are being made, which are directly for either utilizing chemical engineering principles or for chemical engineering applications. Artificial intelligence is used for large-scale process design, material design, catalysts in this particular example, for use in processes, as well as large-scale process optimization. And this is going to be a big, big deal in the 21st century. AI in chemical engineering is going to be a huge, huge deal. Now, getting into strategic defense and space applications, a whole host of sensors, batteries. These batteries, by the way, are made by an Indian company in Trichy called High Energy Batteries. We work with them very closely, not on these battery technologies, but on hydrogen-related technologies. These are, state-of-the-art batteries that are used in our missiles and torpedoes and our submarines and helicopters and aircrafts and whatnot. They are a fantastic company, by the way. In your launch vehicles, your composite rocket motor casing, various propellants. By the way, there are some components in our launch vehicles, PSLV, GSLV, from ISRO that have been developed first principles developed by our department faculty, polymer composite background faculty. And that's a very proud achievement for the department, that every single launch vehicle that is going out has Amrita components for more than past 15 years now. And we are also working very closely on this on developing composites for different end applications. For instance, with our nuclear facilities to be able to store nuclear waste for a very long time, until the half-life and multiple half-lives have crossed, and it's safe to take out those wastes. So there are so many such technologies. So you can see chemical engineers have a huge role to play, and a huge role to shape the 21st century. As successful chemical engineers, if our alumni are, our footprint is extraordinary. We have a global footprint. We have people working all the way up to companies like Intel and Dow Chemicals and DuPont and the world's most leading companies, and to professors in IITs and working in Lawrence Livermore National Laboratory in the University of California, Berkeley, to working in various research organizations, to working in various industries, Reliance onwards, all kinds of industries in India, Indian Oil Corporation. There are people working in IG Car. There's so many places that Amrita's alumni are, and there is a fantastic advantage of Amrita, when you come in and join Amrita to become a successful chemical engineer. Amrita advantage is fourfold. One is we have a cutting edge curriculum. This is recognized by global experts. And we have in our board of studies members from outside. I think right now it's the chairperson of University of California, San Diego Department of Chemical Engineering, and a professor from IIT Bombay, and another professor from IIT Delhi, if I recall correctly. They are all members of our board of studies. They vet our curriculum, and all of them tell us that we have had consistent such feedback that we have a top-notch curriculum. And the biggest proof is in the pudding, right? In the eating of the pudding. So whenever our alumni go for higher studies, and roughly, you look at it, somewhere between 25 to 40% eventually end up going for higher studies. And they all unanimously come back and tell us that, they had a fantastic training here, and that sort of set them apart from their peers from various other institutions, not just from India, but from other places. And that's something that we've taken a lot of pride in and put a lot of effort for that. And world-class research. I was just talking about the kind of collaborations that we have established, setting up joint international centers and collaborations and industrial projects and so on and so forth. That plays into world-class research and global reputation. And all of this comes from the fact that we have a fantastic, highly qualified faculty. At this point, I would like to sort of take a moment to run through another set of slides about our department, which will take just 5 more minutes. And with that, I will wrap up the whole presentation. And I'm not sure if this is being shared, so I should probably go and reshare this. I'm sorry about that. Just a moment. Can one of the organizers please tell me if this is being shared, right? Thank you so much. So this is a brief presentation on Department of Chemical Engineering and Material Science. I'm not going to take a lot of time. I should probably not have the laser pointer on. I'm going to go through the team. The team has a world-class multidisciplinary team. There are about 14, 15 faculty in the department and 5 others who work very closely with the department. So either you will see them as your teachers in some of the classes, or when you are working on research, undergraduate research activities, they'll be very closely working with you, one or both. All right. So there is this thing that you see here called the Center of Excellence in Advanced Materials and Green Technologies, which I head. This is the research arm, a research wing of the department. So basically, this is how we reach out to Amrita, other very closely allied people with similar research areas, and also with a whole host of other collaborators outside Amrita and globally. And of course, this also is a very convenient facility to sort of maintain all our major research infrastructure in one place together. So we have maximum utilization. So this center was set up, and this center, by the way, was set up with funding from Government of India, Ministry of Education. We are one of 33 recognized such centers of excellence by Ministry of Education, and we are the only one in the country in the area of green technologies. And given our efforts in decarbonization, polymer recycling, sustainable environment, energy, and whatnot, it's no surprise. So if you look at the research themes, there are 5 research major themes. All of them are geared towards using or developing advanced materials towards sustainable technologies and devices. If you look at energy materials, as I was just pointing out to you, there is a lot of work happening on hydrogen, solar energies, biofuels, bio-waste to direct engine grade diesel, not just the blended biodiesel. That also is happening, by the way. Okay, so pyrolysis, gasification of bio-waste, and then conversion through what is called a Fischer-Tropsch process to direct petrol or diesel that you can just directly pump into your bike or car or whatever you drive, right? And then a whole host of batteries that are being developed. Okay, so if you go for sustainable resource management, there's a whole lot of work on clean water and soil that I was talking about. One thing I did not focus on is fantastic use of various natural nanoscale adsorbents, which are then further functionalized to remove various pollutants, both anionic and cationic pollutants from water. And then process intensification. This is something very interesting. This is basically improving the resource optimization. How do you utilize minimum footprint, minimum investment, maximum return on investment? That's the kind of concept. So there is a lot of versatility, scalability, and modularity. Microchannels are very, very small channels. And so you have a device that can then, one compact device that's about the size of your palm, your hand, just the palm, and then you have stacks of those. So these kind of concepts, very next generation design concepts. These are technologies that we are developing. These are technologies that we are developing for industries in India and abroad. Bio-inspired materials. Yeah, there you are. So there's a whole host of work on antioxidants, anti-cancer molecules, molecular sensors, a lot of healthcare related work that I was talking about. MRI contrast agents, a lot of organometallic chemistry, which is used for a whole host of applications, ranging from medical applications to fuel cell hydrogen production to electronic devices. And then there is also this fantastic biodegradable sanitary pad, which we'll come to in a moment. And then the last but not the least, again, materials for strategic applications. As I was talking about space, nuclear application, radiation shielding, and recycling that I spoke about. And there's a lot of optimization that happens and modeling that happens in this area. If you look at funding and facilities, we have significant funding from 2014 to present, and we have to add like a whole host of nearly multiple crores that are being now sanctioned by Amrita on top of whatever this number is. So we are going to add to more facilities that are coming. And there is, as I mentioned, this recognition by the Ministry of Education, and then the last one is by Department of Science and Technology, which has cost us major infrastructure developments. And then one of the outcomes of all of this is we've been able to file patents, publish fantastic papers, set up a global collaboration footprint. As you can see, we are practically across the globe. And we have multiple academic programs in the department. Just to last slide, I was talking about this biodegradable sanitary pad. It was awarded most innovative product by National Institute of Rural Development. There is this lemongrass oil distillation, which is solar propelled that was developed by a faculty in our department, which has been installed in rural tribal communities in Kerala in the Wayanad area, and people are using it for producing lemongrass oil, which provides livelihood for them. And this is these kind of activities that you see here, and both the pranavayu and the recycle PPE. These are in line with Amrita's overall, development, not just education for living, but education for life, and research, not just for publications and whatnot, but compassion-driven research, where you take up problems that are relevant, that are directly faced by people around you, and try and solve those problems. And in all of these activities, students are very, very heavily involved. So with this overview of the department, I would like to conclude with just two take-home messages. One is chemical engineering is so broad-based. We are chemical engineers, are universal engineers, that we have a major role in shaping how 21st century is going to evolve. That is the first take-home message. The second take-home message, in order for you to be a successful chemical engineer that shapes the 21st century, Amrita provides very unique, fantastic advantages that we should leverage. And so with that, I invite you to come and join us, be a part of this this growing endeavor. And I wish to interact more with you. I'll be happy to take any questions. Thank you so much.
Thank you so much, sir. Thank you for a very insightful session. I am sure that all the students had a good time and learned a lot about chemical engineering, and all the misconceptions about chemical engineering and what it is ruled out now, I guess. So thank you everyone for watching us, and thank you so much once again, sir, and have a good evening.
Thank you very much. Have a wonderful